Let's talk about improper integrals. Now, I want to remind you, when you took first semester calculus, you saw a definite integral, and definite integrals look like this. You had the integral from a to b, f of x dx, like this. And there's two things that I want you to notice about this definite integral. The first thing was that our region of integration, right, that region was the interval AB. This is bounded. When I say bounded, I mean that interval is of fixed length. It's not of infinite length, okay? The second thing I want you to notice is that f of x is continuous inside that region of integration AB, okay? Now, this section is about something called improper integrals. What makes an integral improper is that one or two is violated. Okay, so we have two main types of improper integrals. Type 1 is basically you have a infinite, I'm going to put the words horizontal region of integration. In other words, 1 here is violated. It's not bounded, it's infinite, okay? And the second, type 2, is that you have a discontinuity within the interval AB. And the way that I think of this is I think of it as infinite vertically. When I say it's discontinuous within this closed interval AB, that discontinuity could exist at either of the endpoints A or the endpoint B, or it could be somewhere inside. So we'll look at some pictures to try to understand these different situations. Let's first take a look at type 1. When we look at type 1, we need to use limits at infinity to handle these type 1 integrals. Okay, so I'm focusing mainly here on type 1. Okay, so let me pause a second to draw a picture. Hold on a sec. Voila, our two graphs magically appear. Okay, so when you take a look at these two graphs, the thing that we're trying to calculate is we're trying to calculate the integral as x goes from a to infinity, f of x dx. So maybe I should have labeled this graph over here as y equal to f of x. And we're really trying to calculate this area underneath this curve over here. But I want you to notice that this goes off to positive infinity. So how do we integrate this? We only know how to integrate definite integrals with finite regions of integration. What we do is we use limits. We are basically going to really create a finite definite integral. Basically, we're going to go from a to t, and we're going to have f of x dx over here like this. And then what we're going to do is we're going to let that upper limit of integration, we're going to take the limit as t goes to infinity. And what that's basically going to do is we have a definite integral over here, and we want to see what happens when we move that upper limit of integration and make it bigger and bigger and bigger and bigger. We want to see, does that definite integral look like it's going somewhere as the as the upper limit goes to infinity. And we're really trying to see if this is a finite number, okay? Similarly, if you look at the second picture over here, this time I called it a different point. I have this point B. It doesn't matter if B is on the left of the y-axis or on the right of the y-axis. The point is that we have an infinite region of integration extending off to the left over here. So when I go to describe this area, we're trying to find the integral from negative infinity to b of f of x dx. And we do the same exact idea. We have the same exact idea. It's the limit as t goes to negative infinity this time. Our upper limit is going to be b. Our lower limit is going to be t. And we got f of x dx. So just as in the A case, we calculate a definite integral, and then we take the limit as we move that left endpoint. We make it further and further to the left. We see, where does this sequence of definite integrals look like it's going? All right. So when either of these limits exist, we say that the improper integral is convergent. And if the limit does not exist, we say the improper integral is divergent. When that limit exists, it's convergent. And when the limit does not exist, it's divergent. There's a third shape as well, a third case. So let me draw this down here. Hold on one second. Voila, a graph magically appears. Okay, so let's say that we have a question where we want to integrate from negative infinity to positive infinity. And that's our function f of x dx. So I should probably label this function as y equal to f of x, okay? So how do we handle a situation like this? Well, what we're going to do is we're going to pick some point from negative infinity to positive infinity. Doesn't exactly matter which one. Let's just cut it right here. We'll call that point A. And what we're going to do to solve this integral is we're going to cut it up into two pieces. So we know that we could split our regions of integration up. So we'll go from negative infinity to A, f of x dx. And then we'll add what we get when we go from A to positive infinity, f of x dx. And when we split our integral up like these two should be equal. And what we'll find is that, oh, this integral on the left, this is the case B we just described up above. And this integral on the right, that's the case A. So we really take case C and we, split that up into case B and case A. And then, you're back to calculating those limits that we had discussed earlier. Okay, so this is just an intro to improper integrals. We'll be looking at examples in class together. All right, everyone, take care.